40 trillion kilometers. This is the distance that light travels in 4 years and 3 months. 40 trillion kilometers of emptiness, radiation, and absolute zero separate us from the nearest star outside the solar system. And here is what should really deprive you of sleep tonight. If we launched a spaceship to Proxima Centauri right now, using the most advanced technologies available to humanity, the crew would arrive at their destination in 73,000 years. 73,000 years in the abyss of space. For comparison, the entire recorded history of humanity spans about 5,000 years. We are talking about a journey that is 14 times longer than everything we have ever recorded, remembered, or passed down from generation to generation. When we discuss the colonization of Mars, we are talking about a distance of 55 million kilometers during the period of maximum planetary approach. This seems incredible. This seems like the limit of the possible. But place these 55 million kilometers next to 4 trillion, and you will understand that Mars is literally in our backyard. Mars is a walk to the neighbor's house. Proxima Centauri is a journey to another continent. Just imagine that between your house and the neighbor's there are no roads, no air, no gravity, and the temperature drops to minus 270 degrees Celsius. Today we will dive into 3 mysteries that will determine the future of humanity as an interstellar species. First, why are our engines, capable of delivering us to Mars, absolutely useless for a flight to the stars? Second, what deadly dangers await any ship that dares to leave the protective shell of the solar system? And third, do technologies capable of bridging this cosmic abyss even exist? Or are we forever locked in our tiny corner of the galaxy? By the end of this journey, you will learn things that are rarely talked about in popular space documentaries. You will understand why the most optimistic scientists secretly doubt the possibility of interstellar flights. You will see numbers that will make you take a new look at our place in the universe. And perhaps tonight, when you close your eyes, you will think about how fragile that thin thread of hope is that connects us to the dream of the stars. If you are fascinated by the mysteries of space, subscribe to the channel. The journey begins right now. Let us start with what everyone knows. The mass media, popular science magazines, and futuristic forecasts paint us a picture of an inevitable cosmic future. Elon Musk talks about a colony on Mars by the year 2050. NASA is planning manned missions to the Red Planet. In the coming decades, China and the European Space Agency are developing their own programs. It seems that space exploration is a matter of time, money, and political will. It seems that technologies are developing exponentially, and what was impossible yesterday will become commonplace tomorrow. This confidence is based on the impressive achievements of recent decades. Rovers explore the surface of the Red Planet. Space telescopes peer to the edge of the visible universe. Private companies are reducing the cost of launches by tens of times. The International Space Station has been operating continuously for over 20 years. Humanity seems to be on the threshold of a new era of cosmic expansion. And when it comes to interstellar travel, the same optimism is transferred to the more distant future. If we can reach Mars in 6 months, people reason, then in 100 or 200 years we will definitely be able to reach the stars. This sounds logical. This corresponds to our experience of technological progress. At the beginning of the 20th century, the Wright brothers' first flight lasted 12 seconds. 66 years later, a man stepped onto the moon. Extrapolating this development curve, it is easy to believe in a future where spaceships move freely between the stars. But the reality is significantly darker and significantly less encouraging. The problem is that progress in space technology does not follow the same trajectory as progress in aviation or computers. The chemical rocket engines we use today operate on the same principle as Wernher von Braun's rockets in the 40s of the last century. Yes, they have become more reliable, more efficient, cheaper to produce, but the fundamental limitations have remained the same. We are still throwing red-hot gases backward to move forward, and the physics of this process sets an absolute ceiling that no engineering improvements can overcome. The maximum exhaust velocity of gases from a chemical rocket engine is about 4.5 kilometers per second. This sounds impressive until you compare it with the distances of outer space. At such an exhaust velocity and taking into account Tsiolkovsky's equation, the fundamental law of rocket dynamics, even a theoretically ideal chemical rocket will not be able to accelerate to a speed sufficient for an interstellar flight in a reasonable time. Here are specific numbers that shatter optimistic dreams to pieces. Voyager 1, launched in 1977, is the fastest object to ever leave the solar system. Its speed relative to the Sun is about 17 kilometers per second. That is 61,200 kilometers per hour. Impressive, isn't it? But at this speed, Voyager 1 will need 73,000 years to reach the distance to Proxima Centauri. 73,000 years. And this is assuming it is flying in the right direction, which it is not. When we talk about the colonization of Mars, we are dealing with a journey that takes from 6 to 9 months one way. This is long. This is risky. This requires huge resources, but it is doable. Astronauts can take enough food, water, and oxygen with them. The psychological burden is significant but tolerable. Maintenance of the ship can be done by the crew. Communication with Earth occurs with a delay of 4 to 24 minutes, depending on the relative positions of the planets. Inconvenient, but acceptable. Now imagine a journey thousands of years long. Not months, not years, not decades, but thousands of years. This goes beyond an engineering problem and turns into a sociological, biological, and philosophical experiment that humanity has never conducted and for which it is completely unprepared. A natural question arises. Why not just fly faster? If current speeds are insufficient, let us develop more powerful engines, build more advanced ships, find new energy sources. Sounds reasonable. And this is where we encounter barriers that are not technical problems waiting to be solved. They are fundamental limitations of physics. Let us break this down in detail. To reduce the flight time to Proxima Centauri to acceptable limits, say to 50 or 100 years, a spaceship must reach a speed that is a significant fraction of the speed of light. 10% of the speed of light is 30,000 kilometers per second. At this speed, the journey will take about 43 years. 5% of the speed of light, 15,000 kilometers per second, is an 85-year flight. These speeds exceed anything we have ever achieved in astronautics by several orders of magnitude. Voyager 1 moves at a speed of 0.56% of the speed of light. To reach 10% of the speed of light, you need to increase the speed 18,000 times. This is not an incremental improvement. It is a qualitative leap comparable to moving from a cart to a space rocket. Well, let us say we find a way to reach such speeds. Let us say some revolutionary engine, ion, thermonuclear, antimatter, allows us to accelerate to 5 or 10% of the speed of light. The problems do not end there. They are just beginning. The first problem is fuel. Any engine requires energy and a working mass. A rocket must carry everything necessary for acceleration and deceleration with it. And the laws of physics are inexorable. The faster you want to fly, the more fuel you need. And this relationship is not linear. but exponential. To accelerate 1 kilogram of payload to 10% of the speed of light using a thermonuclear engine, 1,000 tons of fuel would be required. This creates a paradox. Most of the fuel is needed just to carry the fuel itself. The second problem is deceleration. Accelerating to a huge speed is only half the task. Upon arriving at the destination, the ship must slow down, and this requires the same amount of energy as acceleration. This effectively doubles the fuel requirements. If you do not plan to brake, you will simply fly past the target at a speed of 1,000 kilometers per second, with no possibility to study anything or land. The third problem is the interstellar medium. The space between the stars is not completely empty. There is gas, dust, and charged particles. At speeds of tens of thousands of kilometers per second, even a tiny speck of dust becomes a deadly projectile. A collision with a particle the size of a grain of sand at 10% of the speed of light will release energy comparable to the explosion of several tons of trinitrotoluene. The interstellar medium turns into a continuous meteor shower capable of destroying any structure known to us. And that is not all. Even if we solve the problems of fuel, deceleration, and protection from micrometeorites, a fundamental question remains. Will any human-made structure be able to function for decades or centuries in deep space? Our most reliable spacecraft, the Voyagers, have been operating for almost 50 years, and their systems are gradually failing. Radioisotope thermoelectric generators are losing power. Electronics are degrading under the influence of cosmic radiation. Mechanical components wear out. For an interstellar journey 50 years long, the minimum possible at 10% of the speed of light, the ship must be capable of complete self-repair. It must carry a supply of materials and equipment to repair any part of itself. It must have artificial intelligence systems capable of diagnosing and fixing problems without human intervention. Communication with Earth will take over 4 years one way. No real-time operational support, no consultations with engineers. But the reality is even gloomier than these technical problems, because everything mentioned above applies to unmanned probes. When we talk about manned interstellar expeditions, the complexity increases by orders of magnitude. The human body is not adapted to prolonged stays in space. We know this from the experience of orbital stations. Astronauts spending a year on the International Space Station return with weakened bones, atrophied muscles, vision problems, and changes in brain function. And this is under conditions where the station is 350 kilometers from Earth, protected by our planet's magnetic field, with regular food supplies and the possibility of emergency evacuation. An interstellar ship will be deprived of all this. It will be exposed to cosmic radiation, against which there is no reliable protection with current technologies. It will carry a limited supply of resources that must be renewed through closed life support systems. And it will be so far from Earth that no help could possibly come. Imagine this situation specifically. The ship is halfway between the solar system and Proxima Centauri. That is 2 light years from the nearest civilization. A distress signal will take 2 years to arrive. The response, another 2 years. But no rescue ship could arrive sooner than several decades later. The crew is essentially completely isolated from the rest of humanity. They are on their own in the endless void. And here we come to a question that goes beyond engineering and physics. This is a question of sociology and psychology. How will a small group of people be able to maintain social stability over decades of flight? How to avoid conflicts that in an isolated space could escalate into a disaster? How to maintain motivation and mental health when every day is like the previous one, when outside the window there is only endless blackness dotted with stars? Studies on Earth and Antarctic stations, underwater laboratories, and isolated experiments like the Mars 500 projects show that prolonged isolation has a destructive effect on the human psyche. Depression, anxiety, conflicts, apathy. All this manifests itself even under conditions where participants know the experiment will end and they will return to normal life. On an interstellar ship, there will be no return. For the first generation of the crew, it will be a one-way ticket, not to a distant planet, but into the journey itself. They will die en route, hoping that their children or grandchildren will reach the goal. What kind of person is capable of accepting such a fate? And how do you raise children who did not choose this mission, who were born in a metal box between the stars and will never see a blue sky, green grass, or a sea of people who are not part of their tiny closed world? These questions do not have technical solutions. They require a re-evaluation of the very nature of human existence. And when we honestly look at the entirety of the problems, physical, engineering, biological, psychological, sociological, it begins to seem that interstellar travel may remain forever beyond our capabilities. But wait, all this is based on the assumption that we use principles of propulsion known to us. What if radically different ways of bridging cosmic distances exist? What if warp drives, wormholes, and hyperspace tunnels are not just science fiction, but real possibilities waiting to be discovered? Here we enter the shaky ground between theoretical physics and speculation. Yes, Einstein's general theory of relativity formally allows for solutions describing warp bubbles and traversable wormholes. Yes. Physicist Miguel Alcubierre in 1994 mathematically described a construct that could move faster than light without violating relativity. But there is a significant difference between a mathematical solution to equations and physical realizability. The Alcubierre warp drive requires so-called exotic matter, a substance with a negative energy density. No known form of matter possesses this property. Moreover, quantum mechanics imposes severe limitations on the possibility of such matter existing on macroscopic scales. This is not a problem that can be solved with more advanced technologies. It may be a fundamental prohibition of nature. Wormholes face similar problems. Keeping a wormhole open long enough for a ship to pass through also requires exotic matter. Without it, the wormhole collapses faster than light can pass through it. And if we ever learn to create exotic matter, it will open up possibilities for causality paradoxes, time travel, and the violation of the logic of events. Many physicists believe that these very paradoxes make wormholes practically impossible. Nature simply does not allow such constructs. So what is left? What real, non-fictional options exist for interstellar travel? But the reality is even darker than we dare to admit. There are several ways that theoretically could cross the interstellar abyss. Each of them represents a distinct engineering philosophy, a separate approach to solving the most grandiose transportation problem in the history of intelligent life. And each of them faces its own unique barriers, which as of today make practical implementation impossible. Let us start with ion engines. This is not fiction. Ion engines are already operating on several spacecraft. The Dawn probe explored the asteroid Vesta and the dwarf planet Ceres using exactly ion propulsion. The principle is simple. Xenon, or another inert gas, is ionized, meaning atoms are stripped of electrons and then accelerated by an electric field and ejected from the engine at a speed of 30 to 50 kilometers per second. This is 10 times faster than the exhaust velocity of gases from a chemical engine. The advantage is obvious: higher efficiency in using the working mass. 1 kilogram of xenon in an ion engine provides 10 times more impulse than 1 kilogram of chemical fuel. This allows a significant reduction in the mass of the ship or an increase in its final speed. But there is a critical flaw. The thrust of an ion engine is measured in millinewtons. The engine of the Dawn probe developed a thrust of about 90 millinewtons. That is roughly the force with which a sheet of paper presses on your palm. To accelerate a spaceship to a significant fraction of the speed of light, the ion engine must run continuously for decades. And all this time it needs electrical energy, a huge amount of electrical energy. Where do we get it in interstellar space? space. Solar panels are useless. Already at Jupiter's orbit, the intensity of solar radiation drops 25 times compared to Earth's orbit. Outside the solar system, solar panels turn into useless cargo. Nuclear power sources remain, but the radioisotope generators powering the Voyagers produce only a few hundred watts. This is categorically insufficient for a powerful ion engine. A nuclear reactor is needed, a full-fledged compact reactor capable of operating autonomously for many years. Such reactors do exist. The Soviet Buk program and the American SNAP used them on satellites back in the 70s. But their power was measured in kilowatts, whereas megawatts are needed for serious interstellar acceleration. Creating a compact megawatt reactor capable of working flawlessly for half a century under space conditions is a task that has not yet been solved even on paper. And even if the energy problem is solved, the ion engine is fundamentally limited by the exhaust velocity of the ions. 50 kilometers per second is the ceiling for current designs. Promising developments promise to bring this figure to 100 or 200 kilometers per second, but even 200 kilometers per second is 0.6% of the speed of light. At this speed, a flight to Proxima Centauri will take about 6,000 years, better than 73,000, but still far beyond a human lifespan. The next candidate is the nuclear thermal engine. The idea originated back in the 50s, and in the 60s, the American NERVA project brought it to practical testing. The principle is as follows. A nuclear reactor heats a working mass, usually hydrogen, to very high temperatures, and the red-hot gas is expelled through a nozzle, creating thrust. Hydrogen is the lightest element, and at equal temperatures, its molecules move faster than the molecules of heavier gases. This gives an exhaust velocity of about 9 kilometers per second, twice as good as chemical rockets. The NERVA engine successfully passed ground tests and was ready for flights when the program was shut down in 1973 for financial and political reasons. Today, interest in nuclear thermal engines is reviving. NASA and the Defense Advanced Research Project Agency are funding projects to create a new generation of such systems. They are considered a promising option for flights to Mars. They could reduce travel time from 6 months to 3 to 4. But for interstellar distances, a nuclear thermal engine provides only a marginal improvement over chemical rockets, 9 kilometers per second instead of 4.5. This is not the qualitative leap that is needed. A flight to the nearest star will still take tens of thousands of years. A more extreme version of nuclear propulsion exists, the nuclear pulse engine. Project Orion, developed in the late 50s by a group of physicists led by Freeman Dyson and Ted Taylor, offered a radical solution. Small nuclear bombs are detonated sequentially behind the spaceship. Each explosion creates an impulse that is transmitted to the ship through a massive metal plate, the so-called pusher. Giant shock absorbers are located between the plate and the main hull, softening the impact. Sounds crazy? Perhaps, but the math works. Calculations showed that the Orion ship could reach a speed of about 3 to 5% of the speed of light. At this speed, a flight to Proxima Centauri would take 80 to 140 years. This is already within the bounds of a few human generations. Project Orion was an absolutely serious engineering proposal. The team built scale models and conducted tests with conventional explosives. The physics were confirmed. The only fundamental obstacle was radioactivity. Every launch from Earth would pollute the atmosphere with the products of nuclear explosions. The treaty banning nuclear tests in the atmosphere, underwater, and in space, signed in 1963, put an end to the project. But what if we assemble and launch the Orion ship outside Earth's atmosphere? Technically, this is possible, although logistically extremely difficult. It would require delivering tens of thousands of tons of construction materials and thousands of nuclear warheads into orbit. It would require creating an orbital assembly infrastructure that is orders of magnitude greater than anything that exists today. And it would require political consent to place nuclear weapons in space, which contradicts current international treaties. An even more ambitious option is Project Daedalus, developed by the British Interplanetary Society in the 70s. Instead of nuclear fission bombs, this ship would use thermonuclear micro-explosions. Tiny capsules containing deuterium and helium-3 would be fired into a magnetic chamber and ignited by powerful electron beams, 250 explosions every second. The reaction products, charged particles, would be directed backward by a magnetic field, creating thrust. The theoretical final speed of Daedalus is about 12% of the speed of light. A flight to Proxima Centauri would take 36 years. This is already comparable to the duration of a human career. An engineer working on the project at 30 years old could live to see the ship's arrival, but Project Daedalus revealed the scale of the necessary resources. The ship would weigh 54,000 tons, of which 50,000 tons is fuel. For comparison, the International Space Station weighs about 420 tons. Daedalus is 130 times heavier. Delivering such a mass of materials into orbit would require thousands of launches of the most powerful modern rockets, and this is not even the main problem. Helium-3, which is supposed to serve as the main component of the fuel, is practically absent on Earth. Its reserves in the Earth's crust are measured in kilograms. Project Daedalus required thousands of tons. The only known source of helium-3 in such quantities, the atmosphere of Jupiter and the surface layer of the Moon, where it has been deposited by the solar wind over billions of years. This means that before building an interstellar ship, humanity must create a highly developed space infrastructure, orbital factories, lunar mining complexes, perhaps atmospheric stations on Jupiter. We are talking about centuries of preparatory work before the first interstellar ship can leave the solar system. And what about antimatter, the most energy-dense fuel known to physics? The annihilation of matter and antimatter releases the entire mass as energy. According to Einstein's famous formula, 1 gram of antimatter combining with 1 gram of normal matter releases energy equivalent to the explosion of 43 tons of trinitratoluene. This is millions of times more efficient than chemical fuel and hundreds of times more efficient than nuclear fission. An antimatter engine could accelerate a ship to a significant fraction of the speed of light with a relatively small fuel supply. Calculations show that to reach 10% of the speed of light, a ship weighing 1,000 tons would need about 30 tons of antimatter. This sounds almost realistic compared to the 50,000 tons of fuel for Daedalus, but producing antimatter is a completely different story. To date, humanity has created a total of about 20 nanograms of antihydrogen. That is 20 billionths of a gram. And billions of dollars and decades of work by particle accelerators around the world have been spent on this. The efficiency of antimatter production is catastrophically low. To create 1 gram of antimatter using modern methods would require approximately 25 million billion joules of energy. This is equivalent to the annual electricity production of several small states. And we do not need grams, we need tons. Even if by some miracle a way is found for the efficient production of antimatter, the problem of storage remains. Antimatter cannot touch ordinary matter. It annihilates instantly. It must be contained in a vacuum using magnetic or electrostatic fields. This works for individual antiprotons and positrons in laboratory conditions. But scaling up to tons of antimatter stored over a multi-year spaceflight is a problem for which there is not even a theoretical solution. There is another approach that does not require fuel on board the ship at all, at least for acceleration, This is the concept of a light sail, or solar sail in its original formulation. Light has momentum. When a photon reflects off a mirror surface, it transfers double momentum to it. If you deploy a sufficiently large and light mirror, the pressure of sunlight will gradually accelerate it faster and faster. No fuel, no complex engines, just a thin, reflective film. This is not fiction. The Japanese spacecraft Icaros successfully used a solar sail in 2010 to navigate in interplanetary space. The 14 by 14 meter sail allowed it to develop an additional speed of about 100 meters per second. But a solar sail has the same limitations as solar panels. As you move away from the sun, the light pressure drops in proportion to the square of the distance. At Jupiter's orbit, efficiency drops 25 times. At Pluto's orbit, more than 1,000 times. Outside the solar system, a solar sail is useless. And here appears perhaps the most realistic concept for interstellar flight today, the Breakthrough Starshot project. The idea belongs to Russian-Israeli billionaire Yuri Milner and a group of scientists, including Stephen Hawking prior to his death in 2018. Instead of sunlight, it is proposed to use a powerful laser beam directed from Earth or from low Earth orbit. Laser light does not scatter as quickly as sunlight, and it can be focused on a tiny target millions of kilometers away. The ship, if you can call it that, is a chip the size of a postage stamp and weighing about 1 gram. Attached to it is an ultra-thin sail 4 meters in diameter, made of a material several hundred atoms thick. A laser installation with a capacity of about 100 gigawatts, which is the power of approximately 100 nuclear power plants, illuminates the sail for several minutes, accelerating the tiny ship to 20% of the speed of light. 20% of the speed of light, 60,000 kilometers per second. At this speed, the flight to Proxima Centauri will take about 20 years. The signal with data will return after another 4 years. A total of 24 years from launch to receiving the first photographs of an exoplanet at the nearest star. This sounds incredible. It is indeed incredible in the literal sense of the word. Breakthrough Starshot faces such technological challenges that many experts consider the project a pipe dream disguised as a scientific program. Let's start with the laser installation. 100 gigawatts is about 1/6 of all electrical power generated by humanity. Even if a pulsed mode is used and energy is accumulated over a long time, creating such an installation would require investments of hundreds of billions of dollars and decades of construction. Next, beam stability. Laser light must be focused on a 4-meter target from millions of kilometers away. Any atmospheric fluctuation, any vibration of the installation will lead to beam deviation and loss of efficiency. It is proposed to place the laser in space or on a high-altitude plateau, but even so, unprecedented pointing accuracy is required. Then, sail survival. During acceleration, the tiny ship experiences a g-force of 10,000 units, 10,000 times the pull of Earth's gravity. The human body is crushed under a g-force of 10 to 15 units. Electronics are more resilient, but 10,000 is an extreme regimen even for the toughest microchips. Every component must be designed for these conditions. And finally, communications. A 1-gram chip must somehow transmit data back to Earth from a distance of 4 light years. The most powerful transmitters on the Voyager's output about 20 watts. This is enough for communication from 22 billion kilometers away. Proxima Centauri is 2,000 times further. Even with the most sensitive receivers on Earth, a signal from a 1-gram chip will be indistinguishable from thermal noise. The Breakthrough Starshot project proposes launching not one ship, but thousands, in the hope that at least some of them will overcome all obstacles and be able to transmit at least some data. This is more like a gamble than an engineering project. And all this is for an unmanned probe. A 1-gram chip can carry a camera, a spectrometer, maybe a radiation detector. It cannot carry a human. It cannot even slow down. Deceleration would require another laser installation in the Proxima Centauri system, which obviously is not there. The probe will fly past its target at 60,000 kilometers per second, having only a few hours to gather data. This is the best we can offer today. Not a journey, but a fleeting glance cast during a flyby. Not colonization, not even exploration, just confirmation that the nearest star really does have planets. There are even more exotic proposals. The Bussard interstellar ramjet proposes collecting hydrogen from the interstellar medium using a giant magnetic funnel and using it as fuel for a thermonuclear engine. Theoretically, such a ship could accelerate continuously without carrying fuel with it. In practice, the density of interstellar hydrogen is so low that the funnel would need to have a diameter of 1,000 kilometers, and even then, the resistance of the medium would exceed the thrust generated. Project Medusa suggested using nuclear explosions not behind the ship, but in front, detonating charges far ahead and catching the radiation with a giant sail parachute. This would solve the problem of stress on a pusher plate, but would create new difficulties with targeting and synchronization. The concept of a generation ship completely abandons the idea of rapid flight. A massive, self-sufficient ship, essentially a small world, drifts slowly toward the stars over thousands of years. The crew lives and dies. New generations are born to continue the journey. The final destination is reached by the descendants of those who began the path. This solves the speed problem, but creates problems of social stability, genetic diversity, and technical maintenance. Over millennia, no human organization has ever existed for so long. Empires have risen and fallen in less time. Languages have changed beyond recognition. Religions were born and died. How can the purpose and meaning of the journey be preserved over hundreds of generations? And this is what we arrive at after considering all known options. Ion engines are too slow. Nuclear thermal are only marginally better than chemical ones. Nuclear pulse propulsion requires thousands of nuclear bombs and a decade of orbital assembly. Thermonuclear needs 50,000 tons of the rarest helium-3. Antimatter involves technologies that do not exist and possibly cannot exist. Light sails with laser acceleration require 100 gigawatt installations and a readiness to send a speck of dust to the stars, not a ship. Science is honest. It does not promise the impossible. And the honest answer to the question of interstellar travel sounds like this: we do not know how to do it. We do not know if it is even possible in principle for manned flights. We can fantasize about warp drives and wormholes, but these are fantasies that have no basis in known physics. Perhaps there is a solution out there that we haven't discovered yet. Perhaps in 100 or 1,000 years, physicists will discover new principles of propulsion that we don't suspect today. But making plans based on discoveries that may never happen is not science. It is faith. And for now, we are limited by what we know. And what we know paints a picture of hopeless loneliness in space. The stars will shine above us, unreachable, indifferent, infinitely distant. But technological barriers are only the beginning of the story. Because even if we had a perfect engine capable of delivering a ship to the stars in a reasonable time, the journey would still be deadly. Interstellar space is not empty. It is an arena where forces operate that are capable of destroying any defense we can construct. Interstellar space seems to us the embodiment of emptiness, the black nothingness between the lights of the stars, a vacuum so perfect that it cannot be reproduced in any laboratory on Earth. And this is true. The density of matter between the stars is about 1 atom per cubic centimeter. For comparison, the air you are breathing right now now contains about 27 quintillion molecules in the same volume. The interstellar medium is 27 quintillion times thinner than Earth's atmosphere. But this emptiness is deceptive. It is full of energy, radiation, and particles moving at monstrous speeds. And for a ship racing through this medium at a significant fraction of the speed of light, every hydrogen atom, every dust particle, every photon turns into a potential threat. Let us start with cosmic rays, streams of charged particles penetrating the entire galaxy. These are protons, helium nuclei, and sometimes heavier elements, accelerated to speeds close to the speed of light. Their sources are supernova explosions, pulsars, and the active nuclei of distant galaxies. Some cosmic rays carry energy millions of times greater than what is achievable in the most powerful terrestrial particle accelerators. On Earth, we are protected from cosmic rays by the planet's magnetic field and a thick layer of atmosphere. The magnetosphere deflects charged particles toward the poles, creating auroras. The atmosphere absorbs the particles that still manage to break through the magnetic shield. Only a tiny fraction of the original radiation reaches the surface, and even that contributes to the natural background radiation. In Earth orbit, the protection is already significantly weaker. Astronauts on the International Space Station receive a radiation dose about 200 to 300 times higher than people on the surface. In half a year on the station, a dose accumulates equivalent to several dozen chest X-rays daily. This increases the risk of cancer, cataracts, and cardiovascular diseases. But these risks are acceptable for relatively short missions. Beyond Earth's magnetosphere, the situation deteriorates sharply. Apollo program astronauts flying to the moon in the late 60s and early 70s reported strange flashes of light they saw with their eyes closed. These were not hallucinations. They were cosmic rays passing through their heads and exciting retinal cells. High-energy particles literally pierced right through their brains. The Apollo missions lasted about a week. During this time, astronauts received a dose of radiation comparable to the annual limit for nuclear industry workers. They were lucky. Not a single mission coincided with a powerful solar flare. If that had happened, the crew could have received a lethal dose of radiation while sitting in a fragile aluminum capsule without any protection. For a flight to Mars, the radiation problem becomes critical. 6 to 9 months in open space without the protection of a planetary magnetic field means a significant cumulative dose. Measurements taken by the Curiosity rover during its flight from 2011 to 2012 showed a dose of about 300 millisieverts per flight. This is roughly 600 chest X-rays or 15 full-body CT scans. Add the time on Mars, where the atmosphere is thin and there is no magnetic field, and the return flight, and the total dose approaches the limit set for professional astronauts. NASA sets a career radiation exposure limit for astronauts from 600 to 1,200 millisieverts, depending on age and gender. One flight to Mars and back can exhaust a significant portion of this limit. This means that an astronaut who has flown to Mars will likely no longer be able to participate in lengthy space missions. But the Martian flight is just a warm-up compared to an interstellar journey. Beyond the solar system, the last line of defense disappears, the heliosphere. The heliosphere is a bubble of charged particles emitted by the Sun that extends far beyond the orbit of Pluto. The solar wind, a stream of protons and electrons, creates a kind of barrier that deflects some of the galactic cosmic rays. The Voyager probes crossed the boundary of the heliosphere, the heliopause, and found that the intensity of cosmic rays outside it is about 3 times higher than inside. An interstellar ship will lack this protection throughout the entire journey, decades or centuries of flight in an environment with intense cosmic radiation. And no reasonable shielding is capable of completely stopping the highest energy particles. The problem is that fully stopping a proton with billions of electron volts of energy requires requires meters of lead or concrete. A spaceship cannot carry such mass. This contradicts the basic principles of rocket dynamics. Every kilogram of shielding requires additional fuel, which requires even more shielding, which requires even more fuel, a spiral of hopelessness. Moreover, when a high-energy particle strikes a heavy material like lead, it generates a cascade of secondary particles, neutrons, pions, muons. These secondary particles can be even more dangerous to biological tissues than the original cosmic ray. Sometimes a thin shield is worse than none at all. Researchers are considering alternative approaches. Hydrogen-containing materials, water, polyethylene, absorb cosmic rays more efficiently at a lower mass. Magnetic shields creating an artificial magnetosphere around the ship could deflect charged particles, similarly to Earth's magnetic field. But creating a field of sufficient strength requires huge superconducting magnets and megawatts of electrical power. Yet another technological task with no solution. And here are the specific numbers that are rarely mentioned in optimistic articles about interstellar travel. Flying at 10% of the speed of light, 30,000 kilometers per second, to Proxima Centauri, the crew will receive a radiation dose on the order of several sieverts. One sievert is a dose at which the risk of radiation sickness sharply increases. 4 to 5 sieverts received over a short time are fatal for most people. Stretched over decades, these doses will not kill instantly, but they will significantly shorten life expectancy and increase the probability of cancer, neurological diseases, and cataracts. This means that interstellar travelers will live under conditions of chronic radiation poisoning. They will age faster, get sick more often, and die earlier. And this is assuming the ship's shielding functions at all. But radiation is not the only threat of the interstellar medium. There is something more prosaic and equally deadly: dust. Interstellar space contains tiny dust particles, silicates, carbon compounds, frozen gases. Their size usually ranges from a fraction of a micrometer to several micrometers. This is tens of times smaller than the thickness of a human hair. The concentration of these particles is negligible, approximately 1 dust particle per cubic kilometer. In Earth terms, this is a perfect vacuum. But when a ship moves at 30,000 kilometers per second, every collision with a microscopic dust particle becomes an explosion. Kinetic energy is proportional to the square of velocity. A particle with a mass of a millionth of a gram moving at 10% of the speed of light relative to the ship carries energy equivalent to the explosion of several kilograms of trinitrotoluene. This is not a typo. A microscopic speck of dust turns into a bomb. Upon impact with the ship's hull, kinetic energy instantly converts into heat. The whole material vaporizes, forming an expanding plasma cloud. A shock wave propagates through the structure. Even if the dust particle does not pierce right through the hull, it leaves a crater, weakens structural integrity, and damages protective layers. During a flight to Proxima Centauri, the ship will cross about 40 trillion kilometers of interstellar space. Even at a negligible dust concentration of 1 particle per cubic kilometer, this means millions of micrometeorite collisions. Each of them is a small catastrophe. The cumulative effect can be fatal. The Breakthrough Starshot project we discussed earlier pays special attention to this problem. A 1-gram chip probe flying at 20% of the speed of light must somehow survive millions of collisions with interstellar dust. One proposal is to make the probe so thin that dust particles will pass right through it without having time to transfer all their energy. Another is to use self-healing materials capable of repairing minor damage. A third is to launch thousands of probes, hoping that at least some will arrive intact. For a manned ship, none of these solutions are applicable. A human body cannot be so thin that a dust particle passes right through without consequences. Self-healing of biological tissues has limits, and launching thousands of crewed ships hoping someone survives is ethically unacceptable. There are proposals for active defense. A powerful laser or a beam of charged particles could vaporize dust in the ship's path, creating a sort of tunnel in the interstellar medium. But this requires huge energy expenditures and precise detection of every dust particle from thousands of kilometers away, a task bordering on the impossible. Another idea is a massive shield ahead of the ship, taking all the hits. This shield will gradually disintegrate, but it could be thick enough to last the entire journey. Calculations show that a flight at 10% of the speed of light to Proxima Centauri would require a shield several meters thick made of light but durable material. This adds thousands of tons to the mass of the ship. Again, the spiral of mass and fuel tightens, and we haven't even mentioned larger objects. Interstellar space contains not only microscopic dust, but also rocks the size of a grain of sand, a pea, or possibly even a fist. Their concentration is immeasurably smaller than that of dust. But over a distance of 40 trillion kilometers, the probability of encountering such an object is not zero. And a collision with a millimeter-sized rock at a speed of 30,000 kilometers per second is equivalent to being hit by a tactical nuclear warhead. Add to this the impossibility of detection and evasion. A centimeter-sized rock flying toward you at 1,000 kilometers per second. How will you notice it? Radar is useless at such speeds. The time between detection and impact will be less than a second. Optical systems will not be able to discern a tiny dark object against the black background of space. The only hope is statistics, the probability that the path will be empty enough. But space does not tolerate hopes. It only tolerates calculations, and calculations say that a high-speed interstellar flight is a game of Russian roulette with a very large cylinder. Let us move on to another factor that is often overlooked, the thermal regime. Space is cold. The average temperature of interstellar space is about 2.7 Kelvin, just above absolute zero. This is the relic radiation from the Big Bang, which cooled over 13.8 billion years to the microwave range. Any object placed in the interstellar void far from stars will radiate heat and gradually cool down to this temperature. But a spaceship is not a passive object. Its systems generate heat. The reactor, electronics, life support systems. All this produces energy that must go somewhere. On Earth, we dissipate heat through convection and thermal conduction. Air and water carry away excess energy. In a vacuum, the only way to get rid of heat is radiation. This creates a paradoxical situation. On the one hand, the ship must protect itself from the cold of space, conserving heat for the crew and equipment. On the other hand, it must effectively dump excess heat, otherwise the temperature inside will begin to rise. Balancing heat conservation and dissipation is a complex engineering task. The International Space Station handles this problem thanks to huge radiators, panels radiating heat into space. But the station is in Earth orbit, where the thermal regime is relatively predictable. An interstellar ship will pass through regions with varying gas and dust densities and varying radiation levels, which will affect the thermal balance. Furthermore, at high speeds, the ship itself will heat up from collisions with the interstellar medium. Even a rarefied gas of 1 atom per cubic centimeter at a speed of 10% of the speed of light creates noticeable friction. The front of the ship will be bombarded by hydrogen atoms with enough energy to heat the material to 1,000 degrees. This requires special thermal protection for the nose section, similar to the heat shields on spacecraft re-entering planetary atmospheres. But atmospheric entry lasts minutes. An interstellar flight lasts decades. No known material is capable of withstanding constant heating of this intensity for such a long time without degradation. Now imagine all this together. A ship rushing through the abyss at a speed of 30,000 kilometers per second is continuously bombarded bombarded by cosmic rays, each contributing to the damage of materials and electronics. Microscopic dust particles explode on the surface, leaving craters and weakening the structure. Hydrogen atoms heat the nose section to a white-hot glow. Radiation penetrates the walls, slowly poisoning the crew. And so, year after year, decade after decade. This is not a journey. This is a siege. The ship is like a fortress defending against endless attacks by space itself. And this siege lasts longer than any war in human history. The question arises, why then are the Voyager probes still functioning, having flown for over 45 years? The answer is simple. They move thousands of times slower, 17 kilometers per second versus 30,000. At such a speed, a collision with a dust particle leaves a scratch, not a crater. Cosmic rays have time to partially scatter on their way. Heating from friction against the interstellar medium is negligible, but this safety comes at the cost of time. 73,000 years to Proxima Centauri. This is not a journey. It is a geological epic. We find ourselves caught between a rock and a hard place. A slow flight is relatively safe, but it lasts so long that it loses its meaning. A fast flight reduces the time to acceptable limits, but turns the ship into a target for the destructive forces of the cosmos. There is no golden mean, no compromise that would allow combining safety and speed. And this brings us to another dimension of the problem, the energy dimension. Any acceleration requires energy. Any deceleration requires energy. Radiation protection requires energy. Deflecting dust requires energy. Life support systems require energy. Communication with Earth requires energy. Maintaining the thermal regime requires energy. Where do we get it in the interstellar void? Solar panels are useless, as we have already established. Chemical batteries degrade over time and have a limited capacity. What remains is nuclear energy, the fission of heavy elements, or in the future, thermonuclear fusion. Radioisotope thermoelectric generators, or RTGs, are used on the Voyagers and other deep space probes. They convert the decay heat of plutonium-238 into electricity, reliable, durable, maintenance-free. But their power is low, hundreds of watts at the start of operation, and it drops by about half every 87 years due to fuel decay. For a crude interstellar ship, megawatts of power are needed. RTGs do not scale to such sizes. It would require 1,000 tons of plutonium-238, which is already one of the most expensive materials on Earth. Nuclear fission reactors can provide megawatts of power, but they require cooling systems, control mechanisms, and shielding for personnel from neutron radiation. The Soviet Union launched satellites with BES-5 series reactors with a power of about 3 kilowatts. More powerful space-based reactors exist only on paper. Thermonuclear reactors, the eternal future of energy, promise a practically inexhaustible energy source. But on Earth, despite 70 years of research and billions of dollars in investments, no reactor has yet been built that produces more energy than it consumes. The ITER project in France, the largest thermonuclear experiment in history, plans to achieve a positive energy balance no earlier than the year 2035. And that will merely be a demonstration of the principle, not an industrial plan. A compact thermonuclear reactor capable of operating under spaceflight conditions for decades without maintenance is a technology of the next century or the next millennium. We cannot plan interstellar expeditions relying on inventions that have not yet been made. And so we come to a fundamental contradiction. To reach the stars, we need technologies that do not exist. To develop these technologies, decades or centuries of research are needed. But even having developed them, we will face physical barriers, radiation, dust, temperature, which do not depend on the technological level. The laws of nature will not change when our engineers get smarter. Perhaps interstellar travel is not an engineering problem waiting to be solved. Perhaps it is a fundamental limit established by the very structure of the universe, a limit that separates intelligent life from the stars as insurmountably as the ocean floor separates fish from dry land. And if so, what does this say about our place in space? What does this mean for the future of humanity? What meaning do our dreams of a galactic civilization hold if we are forever locked within our small star system? But before we turn to these questions, we must consider another aspect of interstellar travel, the human one. Because even if all technical problems were solved, a deeper and perhaps more unsolvable mystery would remain. Is the human mind, human society, and human biology capable of surviving a journey to the stars? The human body is the product of 4 billion years of evolution on the surface of one planet. Every cell, every organ, every biochemical reaction is tuned to the conditions of Earth. A force of gravity of 9.8 meters per second squared. Atmospheric pressure of 1 atmosphere. Temperatures ranging from -40 to +50 degrees Celsius. A magnetic field protecting against the solar wind. A 24-hour cycle of day and night. We are creatures of this planet. And our biology knows no other condition. When a human leaves Earth, their body immediately begins to break down. In microgravity, bones lose calcium at a rate of about 1% per month. This is 10 times faster than in the most severe osteoporosis on Earth. Astronauts spending a year on the International Space Station lose up to 20% of their bone mass in weight-bearing bones, femurs, pelvis, spine. This loss is partially reversible upon return to Earth. But full recovery takes years, and some changes remain forever. Muscles atrophy without a load. The heart, which no longer needs to pump blood against gravity, shrinks in size and loses efficiency. Fluids in the body are redistributed without gravity pulling them down. Blood and lymph accumulate in the upper body. The face swells, legs become thinner. Intracranial pressure rises, leading to vision problems. Over half of astronauts report decreased visual acuity after long missions. The immune system is suppressed. Viruses that have laid dormant in the body for years, herpes, chickenpox, reactivate. Wounds heal more slowly. The risk of infection increases, and all this happens in an enclosed space where any virus or bacterium can spread among the entire crew in a matter of days. On the International Space Station, astronauts do physical exercises for 2 hours daily, running on special treadmills with strapped belts, working on strength training machines. This slows down degradation, but does not stop it completely. And this requires special equipment that weighs hundreds of kilograms and consumes electricity. For an interstellar journey lasting decades, simple exercises will not help. Artificial gravity will be required, a rotating section of the ship creating centrifugal force. This is technically feasible, but significantly complicates the design. The rotating module must be large enough so that the difference in force between the head and feet does not cause disorientation. A radius of no less than 200 meters. This increases the mass of the ship and creates additional points of failure. But even artificial gravity does not solve all biological problems. Radiation damages DNA, causing mutations that accumulate over the years. The ship's closed ecosystem, air, water, food, must function flawlessly for decades. Any failure in the water purification system, any contamination of hydroponic farms could lead to a catastrophe. There is another factor that cannot be measured by instruments, and that might turn out to be the most destructive: the human mind. We are social creatures. Our brains evolved to live in groups of a few dozen people, with the ability to move around, with a variety of landscapes and stimuli. We need novelty, change, and contact with nature. We are not adapted to existing in a metal box where every day is like the previous one, where there are the same faces, the same corridors, the same views from the porthole, and endless blackness dotted with stars. Research in isolated environments, Antarctic stations, underwater laboratories, and Martian mission simulations document a predictable set of psychological problems: depression, anxiety, irritability, sleep disturbances, cognitive decline, and conflicts among group members that accumulate and escalate without a way to vent. The Mars 500 project, conducted in Moscow from 2010 to 2011, isolated 6 volunteers for 520 days, a simulated flight to Mars and back. By the end of the experiment, 4 of the 6 participants showed signs of chronic depression. One practically stopped communicating with the others, another suffered from insomnia. And this was under the condition that they knew the experiment would end and they would be free. The crew of an interstellar ship is deprived of such luxury. There is no return for them. They know that their lives will pass within these walls, that they will die here, that their children will be born here and will never see anything else. What impact this knowledge will have on the human psyche, we do not know. We have no precedents. The concept of a generation ship, where the journey lasts longer than one human lifespan, raises even deeper questions. The first generation chose this path voluntarily. They made the decision to leave Earth understanding the consequences. But their children will be born in flight. They gave no consent. They did not choose this fate. Do we have the moral right to condemn people to a life in an enclosed space just because their parents decided to fly to the stars? And what happens to a society over hundreds or thousands of years of isolation? Earth's history shows that even the most stable cultures transform beyond recognition over a few centuries. Languages change, religions rise and fall, political systems collapse. What will keep the society on an interstellar ship from falling apart? What will prevent wars, revolutions, and cultural degradation? Imagine a ship flying to Proxima Centauri for 3,000 years. If the speed is 1% of light, that is longer than the Roman Empire existed, longer than the time from the construction of the Egyptian pyramids to the present day. During this time, the descendants of the original crew may forget where they are flying from and why. They might turn technical manuals into sacred texts and engineers into priests of an incomprehensible religion. Or they might descend into barbarism, losing the knowledge and skills necessary to operate the ship. Science fiction is full of such scenarios, and this is no accident. Writers intuitively understand that the social and psychological barriers of interstellar travel may be higher than the technical ones. But let's assume we have solved all these problems. Let's assume a ship is built with reliable radiation protection, artificial gravity, and a self-sustaining ecosystem. Let's assume methods are developed to preserve mental health and social stability over centuries. Let's assume an engine allows reaching the stars in a reasonable time. There will remain another category of threats, cataclysms on a cosmic scale against which no defense is possible. The universe is a violent place. We live in a relatively quiet corner of the galaxy in a relatively calm era. But space is full of events of such destructive power that they are capable of sterilizing entire regions of space. Supernova explosions of dying stars release energy equivalent to the radiation of an ordinary star over its entire lifetime in just a few seconds. The shock wave from a supernova travels at 10,000 kilometers per second, sweeping away everything in its path. Gamma radiation, neutrino streams, streams of charged particles turn the surrounding space into a radioactive hell. The lethal impact zone of a supernova extends for dozens of light years. Any spaceship caught within this radius will be destroyed not by the blast, but by radiation. The crew will receive a lethal dose of radiation in seconds. Electronics will fail from the electromagnetic pulse. Protection does not exist. There is no material thick enough, no magnetic field strong enough. How often do supernovae occur in our galaxy? About 2 to 3 per century. This seems like a rare event until you realize the scale of an interstellar journey. A flight to Proxima Centauri and back will take at least several decades. During this time, several stars will explode in the galaxy. The probability that one of them will be in the ship's path is small, but not zero. Even more dangerous are gamma-ray bursts, the most powerful explosions in the universe. When a massive star collapses into a black hole, or when two neutron stars collide, the released energy is concentrated in narrow beams of gamma radiation. One such beam carries more energy than the sun will emit during its entire existence. 10 billion years. Gamma-ray bursts are observed daily. Telescopes detect them from distant galaxies. If such a burst occurred in our galaxy and was directed at Earth, it could destroy the ozone layer and trigger a mass extinction. Some scientists suspect that the Ordovician-Silurian extinction event 450 million years ago was caused by a nearby gamma-ray burst. For a spaceship, an encounter with a gamma-ray burst means instant death with no warning. Gamma radiation travels at the speed of light. It is impossible to detect in advance. In one moment, the crew is alive. In the next, their cells are destroyed on a molecular level. And then there are magnetars, neutron stars with monstrous magnetic fields. On December 27, 2004, magnetar SGR 1806-20, located 50,000 light-years away, emitted a giant flare. In 1 second, it radiated more energy than the sun emits in 100,000 years. The flare was so powerful that it ionized the upper layers of Earth's atmosphere from a distance of 50,000 light-years. If such a magnetar were located 10 light-years away, a typical interstellar flight distance, the flare would have been 25 million times more intense. This is guaranteed sterilization of all life within the blast radius. We do not know exactly how many magnetars exist in our galaxy. About 30 are known, but the majority likely remain undetected. We cannot predict when the next giant flare will occur. We cannot defend against it. It is a cosmic lottery, and the stakes are life itself. Add to this black holes wandering in interstellar space without stars or planets, gravitational lenses distorting space, areas of elevated cosmic ray concentrations near supernova remnants, and streams of high-energy particles from distant quasars. Interstellar space is not a void. It is a minefield, and we do not know where the mines are located. And this is what we come to after all that has been said. Distances are insurmountable, speeds are unattainable, engines are inefficient, fuel is insufficient, radiation is deadly, dust is destructive, the body degrades, the mind breaks, society collapses, and space is full of cataclysms. Each of these problems individually might have a solution, albeit theoretical, albeit futuristic, but together they create a barrier that seems absolute, not technical, but absolute, a barrier built into the very structure of the universe. And this forces us to ask a question that goes beyond engineering and physics. A philosophical, existential question, possibly lacking an answer. What if the universe was not meant for travel? We are used to thinking of space as an ocean to be crossed, as a desert to be overcome, as an obstacle between us and our destiny. But what if this is the wrong metaphor? What if the distance between the stars is not a hurdle, not an obstacle, but an isolation, not a barrier to overcome, but a wall separating intelligent beings from each other forever? Think about it. 4 light-years to the nearest star, hundreds of light-years to stars similar to the sun, thousands of light-years to the center of the galaxy, millions of light-years to neighboring galaxies. The universe is huge, so huge that the very concept of hugeness loses its meaning. And in this vastness, we are a speck of dust on a speck of dust in infinity. The Fermi paradox asks a simple question. Where is everybody? If there are billions of potentially habitable planets in the universe, if life arises naturally, if intelligent civilizations develop technologies, why do we not see their traces? Why is the sky silent? Why are there no signals, no spaceships, no signs of engineering activity? One explanation is the Great Filter, some barrier that most civilizations cannot overcome. Perhaps it is a nuclear war, perhaps an ecological disaster, perhaps artificial intelligence slipping out of control. But there is another explanation, simpler and more frightening. The Great Filter is the interstellar distances themselves. Civilizations arise, develop, reach their technological prime, and discover that they are locked in their star systems forever, with no exceptions, because the laws of physics do not allow otherwise. If this is so, we are not alone in the universe. There are many intelligent beings looking at the stars and dreaming of travel. But each of us is isolated on our own island in an endless ocean, unable to reach the neighboring shore. We can send signals and receive answers centuries later. We can build telescopes and observe from afar. But a handshake between civilizations is impossible. A meeting is impossible. We are condemned to loneliness in a crowd. This is a dark thought, but perhaps it contains a grain of comfort. If we cannot reach the stars, then the stars cannot reach us. No aggressive civilization will fly in to destroy humanity. No invaders will land on Earth. We are protected by the same abyss that isolates us. Space is not a battlefield. It is a quarantine. And if we cannot colonize the galaxy, perhaps we should learn to appreciate what we have. This blue planet, this thin layer of atmosphere, this fragile ecosystem that arose over billions of years of evolution. We are not seeds destined to be scattered across the cosmos. We are a flower that can only bloom in this garden. But the human mind does not accept limitations. We look at a wall and see a challenge. We hear the word impossible and start looking for ways. This is our strength and our weakness. This is what led us from caves to space stations. And this is what continues to push us to the stars, despite everything. Perhaps in 1,000 years, physicists will discover new principles that we do not suspect today. Perhaps warp drives and wormholes are not science fiction, but the future. Perhaps the laws of nature contain loopholes that we have not yet found. We do not know the limits of the possible. We only know the limits of the known. But there is another path, a path that does not require overcoming cosmic distances, a path that uses our main advantage, time. Humanity is young. Our species is about 300,000 years old. Civilizations are about 10,000 years old. The technological era is merely a blink. We are just beginning. And if we manage not to destroy ourselves in the coming centuries, billions of years lie ahead of us. In billions of years, a lot can be done. We can colonize the entire solar system, Mars, the moons of Jupiter and Saturn, the asteroid belt, the Oort cloud. We can build space stations that hold millions of people. We can transform planets, creating new biospheres. The solar system is big enough to become a home for trillions of intelligent beings, and we can wait. Wait until the stars themselves come to us. The galaxy rotates. Stars move relative to each other. Alpha Centauri is currently the closest star system to us. In hundreds of thousands of years, it will move further away, but other stars will approach. Gliese 710. A red dwarf in the constellation Serpens will pass just 1 light year from the Sun in approximately 1,100,000 years, 4 times closer than the current distance to Proxima Centauri. Perhaps this will be our chance. And in a few more billion years, the Andromeda Galaxy will collide with the Milky Way. Stars will mix, distances will change. The chaos of the collision could open up opportunities that do not exist today. This is not the time scale we are used to thinking in. Our lives are measured in decades, our plans in years. We are impatient. We want everything right now. The idea of waiting a million years seems absurd, but for the universe, a million years is an instant. For the galaxy, one revolution takes 250 million years. For stars that burn for billions of years, our haste is incomprehensible. Perhaps wisdom lies in accepting the cosmic rhythm, not storming the abyss out of impatience, but waiting until it retreats on its own. But let us return to our initial comparison. Mars versus Proxima Centauri. 55 million kilometers versus 40 trillion. 6 months of flight versus 73,000 years. The colonization of Mars is a challenge for our generation. Difficult, expensive, dangerous, but achievable. We will see people on the red planet in our lifetime or in the lifetime of our children. This is not a dream. This is a plan. A flight to the stars is something completely different. It is not the next step after Mars. It is a leap into the unknown, for which we have neither the technologies nor the understanding, nor even the certainty of its possibility. Mars is a staircase. Proxima Centauri is a chasm over which there is no bridge. And recognizing this difference is not a defeat, it is maturity. It is an understanding of our place in the cosmos, not as rulers, but as guests, not as conquerors, but as observers. We can admire the stars, study them, understand their nature, but perhaps we will never touch them. And here is what remains after all that has been said. The question is not whether we will fly to the stars. The question is who we want to be. A race forever striving for the unattainable and suffering from its limitations. Or a race that finds the infinite in the small, that sees a miracle in every sunrise on the only planet we have. Space is silent. The stars burn in the endless distance, and we, little creatures on a little planet near an ordinary star, on the edge of an ordinary galaxy, ask questions to which perhaps there are no answers. And there is no tragedy in this. There is beauty in this, because the very ability to ask these questions is a miracle. The universe looks at itself through our eyes. The universe becomes aware of itself through our minds. We are the cosmos's way of knowing about its own existence. And even if we never leave this tiny dot in infinity, we have already made a journey of understanding, a journey of awareness, a journey from primal fear of the lights in the night sky to the knowledge that each of these lights is a sun with possible worlds. Tonight, when you close your eyes, think about this. About the distance of 40 trillion kilometers, about 73,000 years of flight, about barriers that may be insurmountable, and about how, despite all this, or because of it, every glance at the starry sky remains an act of infinite courage. The courage to admit our smallness, the courage to continue dreaming, the courage to be human in a universe that is not obligated to care about our dreams. The stars will shine for billions of years after our civilization fades. Galaxies will swirl in an eternal dance long after the last human disappears. The universe will not notice our absence. But while we are here, we can notice it. We can admire it. We can try to understand. And this is the only immortality available to us. Look at the stars. They are unreachable, but they are visible. And that is everything.